Okay, today we're going to be looking at friction. Friction is obviously something that opposes motion, and strangely friction is linked to the reaction force, and we actually have an inequality. Friction is less than or equal to mu r. Mu is just a constant, so it's some multiple of the reaction. Why is it less than or equal to? Because what happens as we begin to potentially move something or other, the value of friction can go from 0 up to a limiting value. The idea is at the moment, in this situation here, even though my table is not perfectly smooth and the back of the board isn't perfectly smooth, there's no friction because the only forces acting on each of these boards is the reaction and the weight. There's nothing acting horizontally at all. When I begin to tilt it though, there'll be a weight component acting at an angle, and that then will have to be balanced out by the friction. If the angle's too steep, then we can have some sort of motion for if the boards themselves or if something is on the board, and that's because we've gone beyond our limiting value of friction. Friction will not always just balance out the weight component, and so we have what's called a limiting value. But what about mu? Mu is just a constant. It's not got any units. Examples of what mu could be, if it's between two random pieces of wood, mu is about 0.4. Between your car tyre and the road, mu is about 0.8. Sandpaper to sandpaper is quite a rough pair of surfaces. Mu is approximately 2.0. Skis on snow, very slippery indeed. Mu is very small, 0.02. Mu is never going to be negative, by the way, just so you know. That'd be a bit weird. So let's look at a couple of examples and see what's going on. So in this case here, we've got a reaction force because we've got a body in contact with the surface at a weight of 2g. There's a 4 Newton force going horizontally. The thing is just on the point of sliding. And the question is, what's mu? So what's missing from the diagram is my friction. So all I'm going to do now, I know that friction is equal to mu r. So as long as I can find r, so I'm going to resolve upwards. Say r is equal to 2g, 2 lots of 9.8, 19.6 newtons. I know that I'm going to resolve that in this way because it's balancing out, it's in equilibrium, then friction will equal 4. So what is mu then? If it's on the pointer going, mu will equal friction over r. Friction is equal to mu r as rewritten in this case, so it's 4 over 19.6, which is about 0.2. So what it is, 4 divided by 19.6 equals 10 over 49, 0.204, 0.20 does the job there. I can use up to 3 different figures, but nothing more than that. No units, just no value. If that 4 newtons wasn't 4 newtons, if it was 2 newtons, friction was still equal 2. But it wouldn't be on the point of sliding. This value of mu isn't changing at all. It's not going to be a smaller value of mu because it's a smaller value of friction. That's the value between these two surfaces. So in the case when I'd work out r to be 19.6, mu r, the maximum value friction can take is 4 newtons. If that force would have been smaller, friction would have still been equal to it because it's not going anywhere, but it wouldn't necessarily have to equal exactly 4 newtons. If that force going that way is bigger than 4, then we've got motion. We're going to have a resultant force horizontally. The thing's going to be moving. If that's 5 newtons, maximum value of friction is only 4. We'd have a resultant of 1 newton horizontally. We've got motion. It's accelerating. But we'll come to acceleration some other time. Second example, we're given the value of mu, 0.3 in this case. We're given the mass, 5 kilograms, so the weight's 5g. We're given the tension, 20 newtons, an angle of 30 degrees. And the question is that enough to make it move or not? So it's not necessarily in equilibrium. So there's my friction. What I can do in this case, I can work out what the maximum value of friction is going to be, because I can resolve upwards to work out r. That equation would not have friction in it. I can work out the value of r, I can times it by 0.3, I can work out the maximum value of friction, I can compare that with the horizontal component of this 20 newton force. Talking of which, to help me resolve vertically, and because I'm going to use it later on, I'm going to extend this and write on my diagram the horizontal component of the 20 Newton force. It is 20 times cos of the angle that we go through, which is 30 degrees. Why is that useful to me to write it there? So that when I look to go vertically, my upwards forces balance out, so R plus the component of 20. If that horizontal one's 20 cos 30, this has to be 20 sine 30. Sine 30 to half, so 20 sine 30 is 10. So I know we've got R plus 10 equals, what's going down? 5G. 5G, nicely, 49. So R equals 49 minus the 10, 39 newtons exactly. Now horizontally, if it's moving, then the 20 cos 30 will be bigger than the maximum value of friction. Well, friction max, because it's potentially moving, is going to be 0.3 times 39. 3.9 times 3, 4 times 3 is 12, 11.7 newtons. Whereas 20 cos 30 is 20 lots of root 3 over 2, 10 lots of root 3, 17.3 newtons. And since that is bigger than 11.7, then we have motion going that way. We have a resultant horizontal force, so it's in motion. The biggest friction can be is 11.7. This horizontal force is bigger than that, so we're moving. Last example, in this case, we've got body mass 16 kilograms. We've told mu is 0.35. We've got a tension at 18 degrees below the horizontal, and we want the maximum value of T, so there isn't any motion. Okay, so I can do similar-ish. Now this is going to be a bit of a mess. I can use my diagram to say that's T cos 18. And how it's going to go is this. When I resolve in both directions, horizontally and vertically, I'm going to have T appearing in each one. Because I'm after the maximum value of T, I can use friction equals mu r in this case here. What's going to happen is, well, we'll see. If I resolve horizontally, I know that this way I've got T cos 18, and the other way I've got friction. So I can't solve it to find either friction or T at the moment. When I resolve vertically, I've got R going up equals 16G plus, since that was T cos 18 horizontally, this is T sine 18 degrees there. And I'm going to be using friction is equal to mu r because I'm after the maximum value of T. So friction is T cos 18 equals 0.35 times 16G plus T sine 18. Now although this looks like a mess, it's no different than solving an equation like that. How would I do it? Move the x's across. 5x minus 2x is equal to 7. 3x is 7. X is 7 over 3. And we'll do exactly the same thing. Move it across. Take t out as a common factor. Cos 18 minus 0.35 times sine 18 equals whatever 0.35 times 16G is. And T is 0.35 times 16G over whatever cos 18 minus 0.35 sine 18 is. There's no cancelling down, just because I've got 0.35s appearing somewhere in the top and the bottom. It's not common. So press my buttons at the very, very end, remember. So fraction button, type it as it is. 9.8, and then I've got cos 18 there, minus 0.35 sine 18 there, press equals 65.1 or 65 newtons. Okay, so in that case there, I'm checking because I've got 2SF, I can quote 2 or 3. I couldn't be quoting any more than 3 significant figures. I'd lose a mark for accuracy if I did that. So 65 or 65.1. The problem you're going to have with mechanics questions at this stage is that this is basic algebra, but with awkward coefficients. The method is no different than over here. All I'll be doing is tidying it all up, getting everything with my unknown on one side, everything else on the other side, factorising it, and then divided by that. And I've done no different there than here, but obviously that looks a bit neater than this mess here. I try and leave my button pressing to the very end, because otherwise I'm rounding off and making rounded off errors. So that's how we deal with friction as a limiting value, friction being less than or equal to mu r.